Hey, how's it going? Good to see you all again, even if it's under these circumstances. It's Alan here, going over some more identities, but this time gonna have to take quite some time to actually derive the sum and difference, and we're gonna start with cosine this time. So bear with me, try to follow along as best as you can, and hopefully it'll make sense why they are what they are, and then we'll learn how to use them in various ways with some examples. So here we go. So you can see in this section, we got a lot going on here already. But basically what we're going to be starting with are these identities called the sum and the difference for two angles. And again, like I mentioned before, we're going to start with cosine instead of sine. All right, so we're going to start with this unit circle. As you can see, we have a unit length from our center, our origin of this circle. And if we went straight to the right, it is a point P, we're going to call it, of 1, 0. So this is the unit circle because it's a length of 1 for our x. Now don't forget, we also mentioned that if we're dealing with the unit circle, we know that cosine of any angle is equal to x over r. And since we're on the unit circle, that means our r would be 1. So we're talking about x being equal to cosine. And similarly, if we did it for sine of any of these angles, it would be y over r, or just y, since we're on the unit circle. So if we wanted to rewrite these things in different terms, instead of some x comma y, which this one we know, so we might as well put it because it's much simpler. What if we said some other x and some other y? Like, let's go to this point Q here. Well, then if that right there to get to that point Q is how we're going to denote this specific angle, which we're going to call B, then this angle right here, which makes up that arc to get to this point Q, then we know that the x value would be equivalent to cosine of that angle B. And so this would be the x, and same thing for the y value, that would be the sine of that particular angle, which we are calling B. Now you may be wondering why we started with B rather than A. Well, because what we're trying to find are sums and differences. And I'm going to start with the difference because you know when we subtract angles, it gets smaller rather than getting larger. So the first angle that we're going to be dealing with is B here to get to that point Q. So our x is cosine B, our y is sine B. But then the larger angle to get to here, we're going to call A. And that value, A there, would take me all the way over here, which therefore this point, we're going to call the next letter S. So S would be the next one that we're dealing with. And therefore, my x value would be the cosine of that angle, and the y value would be the sine of that angle, which we said was A to get there. So if we were to take that big angle A, that obtuse angle, and that smaller angle B, and we subtracted that off, if I took this angle here and rewrote it over here, then you can see that this is angle B and this is angle B. And if I subtracted that off of the larger angle A, then what we would be left with is this blue one here, which would be the larger A minus B. If we subtracted off this part right here, which is B, then we would be left with this, which was our A angle all the way over there, less the B, which was here, and therefore we would be left with the A minus the B to get to this point R. So that is the angle A minus B, which means our angle is therefore the A minus B, but our x value is still cosine of that angle, and our y value is still sine of that angle. And you might be wondering why, right? Why are we doing this? Well, hear me out. This is where it gets a little weird if it hasn't for you already. I know that this blue one here is definitely by definition, the way that we wrote this, we defined it, was the angle A minus B. And if I was to take the end point from the beginning point, and I was to measure that distance between those 2 points, between R and P we called it, that is actually what is called a chord, or a segment, but of a circle from one endpoint to another, not going through our center, we call that a chord. And if I was to find that distance of this segment, this chord, then we should be able to do that. Hopefully you remember the distance formula is simply between any 2 points, the square root of x2 minus x1 squared plus y2 minus y1 squared. So that is the distance formula between any 2 points. Now our x's and y's look a whole heck of a lot different. That, not so much. But everything else, that x, that y, that x, that y, this and that, very much different than what we're accustomed to. But hey, it's trig after all, right? We got to throw a little bit of a curveball at you. But remember we talked about the distance from the angle A minus B from the 2 endpoints would be what we call RP. But remember what the one in red was. This one here. Remember this was all the way over to A. And what this blue one was we subtracted off that B there. And so we knew that this angle was A minus B. But if this right here is B, and all the way over here was A, then if we subtracted off the B from the whole thing that makes up A, then this too would also be A minus B in red here. And therefore, if the blue one, which we already said here, was due to the arc or angle A minus B, then this distance between its endpoints, which we called RP, should therefore be equivalent to this one, which is also A minus B, that arc, that angle. And so if we took its 2 endpoints and drew that segment, or what we call in a circle a chord, then if I drew that one in, then that, which we're going to call SQ, should also have the same distance. And so remember I reminded and refreshed your memory here that this is how we find the distance between any 2 points. Whether our x's look like 2's and 5's or negative 3's and 1's, like they always had been in algebra. Now they look like cosines and sines of various angles, whether they're A's, B's, or A minus B's. So using this and plugging it into each of these individually would yield distance between R and P, those 2 points, which were in blue there, would be my x2 minus x1, which was the cosine of A minus B minus the 1. And then that squared plus my y2, which was the sine of A minus B, minus y1, which was 0. That whole thing squared. And don't forget it was the square root of all of that. By definition, if you need to review, go ahead, but that is the distance formula between any 2 points. Our points are just quite different than what they normally look like. Then taking the S and Q points, which had that same angle A minus B as the blue one did, we'll take the x2 minus the x1, that whole thing squared, and then plus the difference in my y values, which was sine A minus sine B squared. Now, what we're going to try to do is take this equation and simplify it, make it look a whole lot better. Now, obviously, one nice thing is that they're both square roots on either side, so the very first thing we can obviously simply do is just square both sides to get rid of those. So that would then take care of this, and that take care of that. Now, what I'm left with over here is the cosine of a minus b minus 1 quantity squared, plus when I subtract 0, I'm just left with this. So the other one would be sine of a minus b. That angle, the argument, we call it squared. And it would be equal to the other side. And so our next step is to obviously square and expand out to see if we can rewrite this in a little bit better form. So our next step would look like this. And now that I've color coordinated and expanded or squared this out by writing the cosine a minus b minus 1 times itself, I'd get cosine squared of that angle minus 2 times of those plus 1. And then squaring that, since there was only one thing in there, even though that looks like 2, we're just squaring sine of that angle. So we get sine squared. On the other side of our equal sign, we expanded this again to look like the cosine of a minus cosine of b times the cosine of a minus the cosine of b. So that would leave us with cosine squared minus 2 times those things, and then plus cosine squared of angle b as well. And then similarly over here with sine, sine squared minus 2 sine a sine b plus sine squared of b. And now obviously we want to move some things around to see if we can get these to either cancel out or look a whole lot nicer. So I'm going to do some rearranging, and then we'll start moving some stuff. So explaining that next step, notice I'm going to see a lot of squared sines and cosines. And just working on the left side of my equal sign, remember we talked about them being, when they're squareds, the Pythagorean identity we should be looking for. Now remember, the one caveat is we have sine squared plus cosine squared. It has to be of the same angle in order for it to equal 1. And if you notice, I circled here, I have a sine squared plus a cosine squared of the same angle, happens to be a minus b. So therefore I said that these two things actually equal 1. So I can replace all of that, those two things, with a 1. I still have then this one, which then I wrote here. So there's that one. And then the negative 2 cosine of a minus b I brought straight down to still be there. So cleaning that up, I would have 1 plus 1, which is 2, minus 2 times the cosine of a minus b. Looks a little better already. Now on the other side, there's 2 different sets of these. One is the sine squared of a plus the cosine squared of a. So there's my first pairing, that is a 1. And then I have another, which is the cosine squared of b and the sine squared of b added together. So those two together were another 1. Now unfortunately, whatever was left was left. So I just brought down the negative 2 cos a cos b and the negative 2 sine a sine b. And this is what's left. The only pairings that I can do is the 1 plus 1, which is 2. So that together with everything else leaves me with that. So next, I hope you notice that there are definitely a lot of 2's. So the first thing I'm going to go ahead and do is subtract the 2 to both sides so that that cancels out. And we can do that because there's an equal sign. And then lastly, I'm going to go ahead and divide the left side and the right side all by a negative 2 to get rid of that. And that would then yield a positive 2 over 2 is 1. So I get the cosine of this angle a minus b is equal to that negative 2 over negative 2 also becomes positive 1. So we get the cosine of a times the cosine of b plus, that would become a 1. So plus 1 of our sine a sine b. And unfortunately, my friends, that is the best that we are going to do. But remember, what we initially set out to do was find the sum or difference of 2 angles for cosine. So if you were wondering why, if I was just to give this to you, that these 2 things were equivalent, now you know. And sometimes you may be also wondering why we would ever take one thing and separate it into these four, these two and these two being multiplied together and then added. Well, that's because we may not know the cosine of this angle, A minus B, for example. But we may very well know each individually, the sine and cosine of A or the sine and cosine of B. So just to give you a quick example, we won't actually work it out yet, but that would be like the cosine of 15 degrees. We don't know that one without using technology. But what I could rewrite that as is the cosine of two things that I do know, 45 minus 30. Now notice what did not change was the fact that I have a 15-degree angle. So remember, we can't change what we have. We can only change the look of what we have. And that would then allow me to write my A and my B for each and every one of these, because we know that these are our reference angles on our unit circle. Okay, so there is a rhyme and a reason for all of this, all right? But I wanted to show you at least once why that is the way it is. And again, I hope that you were able to follow based off of our unit circle and evaluating these x's and these y's according to different angles, a B and then an A, and then the difference of them actually twice. Okay, so again, that's something that I think is valuable for you all to see why these things are the way they are. Like in my pre-calculus or algebra courses, I always like to go over and show everyone the derivation of the quadratic formula, because a lot of people know it, but they don't know why it is what it is, and it's really not that hard to derive. Okay, so I'm just going to quickly use this to then show you what the other one is, the sum of two angles for cosine, by getting a little creative and rewriting this B here, and then start utilizing these with a few examples. So now that we have that difference identity for cosine, we're going to use that same thing by, again, getting a little creative and rewriting, instead of A plus B, we're going to rewrite our A plus B to be a double negative. All right, so that means we then have the cosine of the first thing, the A, minus the second. And if you guys remember, cosine of any angle was the x over the r, or on the unit circle, it was the x. And remember when we were graphing last chapter, we talked about the x's being the opposite. So that's how you can know what sign goes in between these things. All right, just like we derived up here. Notice it was a minus here, but we ended up adding here. And remember, this is for cosine. So you have the cosine of the first and second angle plus the sine of the first and the second angle. All right, so when we're deriving this, we'll start by putting the cosine of the first times cosine of the second, which remember for this one, it was a negative b. And then because it's a minus, we'll do the opposite because it's cosine, so we'll put plus the sine of the first times the sine of the second. Now, if you remember, we also discussed negative angles were, because we much prefer positive. So the A's, all good. Those are going to stay the same because they're already positive. But the negative angles, and we call these even and odd identities. What would it be for cosine? Remember, even though technically it goes from quadrants 1, 2, 3, all the way to 4, we're just going to stay in quadrant 1 and talk about that negative b angle being there. Because then we'll, when we do the negative b, go into quadrant 4. And we know for cosine that would stay positive, but for sine it would change to negative. So that yields it being a cosine of A times just the cosine of B. We know that this is the same as that would be as far as our ratio coming out. Whether it's positive b or negative b, we get the exact same values, positive. Okay? But for sine, we know we'd get the opposite. And so we're going to bring this negative out in front. And since this is multiplying with that, and this is a positive, and this would become a negative, then rather than having to write a big parentheses around and putting that negative there, we're just going to move it out in front. So that is now going to be the positive times the negative. So negative sine of A sine of B. And that then is what the cosine of A plus B, or the sum formula or identity for cosine is. So that's what we have for the cosine of A plus B. We just got the cosine of A minus B right there. And again, one more time, just to help you to start memorizing these things. Remember, for cosine, it's going to be cosine of the first two angles. And then remember, cosine is the x. So it's going to be the opposite sign for each of these times the sine of each of my angles, A and B. All right? Not too bad. Again, the first one took a lot longer to initially start, but once we had that, we were able to manipulate it creatively to get that plus sign there that ultimately we wanted to find. So there it is, all written out for you, side by side, stacked. And as a reminder, remember the argument or the angle, if it's A minus B, that's together. This is a function, and you cannot distribute a function and say that it's equal to this. Okay? Make sure that you make a note of that, or at least don't do it. All right? So one more time, remember that cosine of an A plus or an A minus B is always going to be the cosine of the angles with the opposite sign, because remember it's the x value, times the sine of the two angles multiplied together. Okay, so remember cosine, and the signs will be opposite. Well, in order to kind of go through this proof and help you out, how are we going to get sine involved? Well, remember, cosine is the cofunction, we called it, the complementary function. And remember, complements are when they add up to 90. So I know that the cosine of 90 minus an angle is equivalent to the sine of the angle. Because if you notice, if I took this and added it to that, the negative and positive thetas would cancel out, and we would get that sum of 90 that we said. So just to refresh your memory, what I just went over, these were called cofunction identities. Okay, if we have 90 minus an angle for cosine, we know that that is the complementary angle to sine, that function for that angle. Okay, and if cosine works that direction with sine, then it also should work the other direction for sine and cosine, as well as tangent and cotangent, or secant and cosecant. Okay, and of course, if they wanted to use radians, we could rewrite the 90s with what we know is equivalent, and that's pi over 2. And as you can see here in my quick notes that I wanted to mention, there's an infinite amount of solutions to a lot of these. A lot of times we're only going to give one. Okay, so speaking of one, that takes us to example 1. And if you want to go ahead and pause, you feel good about this, or you want to even go back and review and make sure that you understand what all of those are, so that we can then use them to solve, as you can see here, for the exact values. If they want an approximate, punch it in your calculator, not a lot of thought to it, you're done. So I gave you a couple here with both degrees and radian measurements for our angles, the argument we call it. And then I gave you a longer one, which, by the way, is actually the easiest one. So give these a try real quick, come back, I'll go over them with you, and we'll move on to example 2. All right. Shouldn't have been too difficult to do, especially if you took my advice and memorized all the unit circle special values we call reference angles, the 30s, the 45s, and the 60s for both sine, cosine, and tangent. If you know those, then you can do the reciprocal and you automatically know the cosecants, secants, and cotangents as well. So starting with the first thing, I want to make a note. If you want to do this, go off to the side and make sure that you put this down. Make sure that you do not change what's given. A lot of students will start manipulating these, but they change what was given. They want to know the exact value of the cosine of 75. Well, then guess what? You can't change that 75 or that cosine. So what we can do, though, is we can rewrite it. Now, we're not going to have to multiply by a 1 in this case, but we can separate 75 in any way that we want, as long as it stays 75. So what I'm going to have to do is think about two numbers, which obviously this one should be pretty easy. I gave you an example earlier of it, that combine to be that 75 degrees that they gave us. That also is something that I can evaluate. We're looking at all those special things I harped on at the beginning of this class called reference angles, the 30s, the 45s, and the 60s, and all the multiples of them all the way around in quadrants 1, 2, 3, and 4. We're going to use all of those. I'm just starting you off with something easy for example 1. So once you have that, you're pretty much done. You've rewritten the 75 as two things that you do know how to evaluate. But now, the hard part, you're going to have this memorized. And by this, I mean, what is the cosine of 30 plus 45 equivalent to? Identical to. We call it an identity. Remember, you just got to see this as the A plus B. And so I know that the cosine of A plus B is the cosine of each of those. And then remember, cosine was the x over r. So we're going to take this and we're going to do the x opposite. And now we're going to do the sine of each of those angles. And once I have that, then all I have to do is evaluate. Now I say all because it should be very, very quick by now. Okay? We should already know this, that, and that. So we just need to take those four values, multiply together, order of operations, right? Parentheses first, then exponents, which we don't have any. Then we'll do the multiplication before we add or subtract. So what is the cosine of 30? You need to know it's root 3 over 2. And if you know it like that, then you'll be a whole lot quicker at getting this done than others. Okay, hopefully you're not looking it up. Cosine of 45, root 2 over 2, which means the sine of 45 is also root 2 over 2, and the sine of 30, easiest one to remember, is 1/2. So all we are tasked with doing to finish is multiplying each of those pairs before we subtract. So multiplying straight across, a square root times a square root will still be a square root. 3 times 2 is 6. That is not a perfect square. We can't factor it down into any pairs under there, so that stays. On bottom, 2 times 2 is 4. Minus 1 times root 2 is root 2, and 2 times 2 is 4, which is really nice because we actually have a common denominator already set up. So I will keep it and do what it says on top, and that says to take the square root of 6 and subtract the square root of 2, but you can't. You cannot subtract those and say you have the square root of 4, okay? You know the square root of 4 is 2. Do me a favor, if you want to argue this point, take the square root of 6 in your calculator, punch that in your calculator, then take the square root of 2, punch that in your calculator, and subtract them. I can guarantee you it is not equal to the square root of 4 or 2. It is definitely not equal to that. Okay? So unfortunately, or fortunately, however you want to look at it, you're done. There's nothing else that you can do. So there's our answer to part A. Okay, if you feel a little bit more confident now, you want to go back and try part B because you got stumped on part A, go ahead and pause it and do that. If not, here we go. So with this one, it's a little bit harder because they gave us the cosine of radian measurement. But if you do not like radian measurement, it's okay to change it as long as you don't change what was given. Which means as long as I keep that value, if you'd rather rewrite it as a degree measurement like we had over here, then do it. You should know the one thing that you have to do for that is take that 7 pi over 12 and multiply it by a 1. And which one? Well, remember we want to get rid of the radians, which we know that there are pi radians in 180 degrees. And if we do that, then what happens? The pi's cancel out. And remember, we don't technically need to write radians. I just wanted to make sure you knew what went where. The angle measurement degree is what we wanted. So either punch this in your calculator or you can do by 6 really easily. 6 goes into that twice, 6 goes into that 3, and then 0 times, and then 2 goes into 30, 15. So I have 15 times 7, which I know 7 times 10 is 70, and 7 times 5 is 35, for a total of 105 degrees. So effectively what we are trying to figure out is the cosine of 105 degrees. Those are equivalent. So whether they give it to you like this and you'd rather rewrite it, or you'd rather just try to figure it out using the pi over 12. Now remember, the 30, the 45, and the 60 can all be written in terms of pi's. You just had to remember which ones went with what. The easiest one to remember is that 45 was the one that was a 4. And then the 60 and 30, which are complementary to one another, since they're complements, they complement each other. So the 3 would go with the 6, and the 6 would therefore go with the 3. So already you can see that I'm probably thinking it's these two in some capacity because I know 4 times 3 gives me the 12. We're just going to have to multiply this by a 1, so 4 over 4 to get my 12, and then this by 3 over 3 to also get my 12. And that's going to give me different multiples, a 4 and a 3 for a total of 7. So there it is. You can use either way. Most people prefer just changing it to degrees because that's what they're most comfortable with. That's what they learned first. So that's why I just wanted to mention this as a side note. We'll continue forward with the degree measurement and changing it from radians to degrees. So when I see a 5, I immediately know that a 45 is going to have to be involved because it's the only one that ends with a 5. The other two, whether you're adding or subtracting, would never be able to get you to that. And what do you prefer typically? Adding or subtracting? Yeah, most people do. So I know it's going to be a 45 plus how much more to get to 105? If you said 60, well done. So remember, you cannot change what's given. And we did not. We just simply changed the look of it so that we can now evaluate and get our next step, which would be cosine of A, cosine of B minus the sine of A times the sine of B. All right. Once you have that, then we are tasked with evaluating each one of these 4 values, which again, if you took my advice and memorized, done. Super quick and easy. You should have got cosine of 45 and the sine of 45 are both the root 2 over 2's because they're the one, the 45, that has the 2 angles the same. The 30s and 60s have the root 3's involved. And if you remember that the sine of 30 is 1/2, then so is the cosine of 60. Complementary. Cofunctions, we call them. Okay? Now, of course, you're going to see a lot of the same values. So when I go to multiply this across, I get the root 2 over 4 here, and then here I'd have the root 6 over 4. So those look very familiar to what we got over here. So be really, really careful when you're taking the quiz or the test that you pay attention to the ordering of these things, because it does definitely matter, as well as the signs. You may have a multiple choice question and they all pretty much look the same, but the signs will be different and the ordering of the root 2's and root 6's will be different. Maybe even the denominator to try to throw you. Okay, so really pay attention to details. The final answer to this one should have been that. So again, not too difficult, but different, right? It's going to take some getting used to, but hopefully you guys are getting a little bit more comfortable already. Example 3 is just working backwards. They still want the exact answer to this one, but what would it look like? Well, hopefully you can see that it's already written as, so we're just working backwards to be able to now write that as, hopefully you notice it's cosine of, since it's cosine, the angle should be different. So it's going to be the A, which is 173 degrees, minus the B, which was the 83 degrees. And if you do the 3 minus the 3, that's going to zero out. And what is 17 minus 8, or 170 minus 80? Either way, hopefully you said 90 degrees. So this is just a different way of writing 90 degrees. And of course, remember at the beginning, they asked us to evaluate what it is exactly. So that means that we're going to have to say what this is equal to if we know it. And you should definitely know this one because it is a quadrantal angle. So we're just going to be right here, which is the point 0, 1. And because it's the cosine on the unit circle, we're going to say that that is equivalent to the x, which would be a value of 0. All right, hopefully that made sense to you. Not too difficult, but again, different.